Hey everyone, welcome to this explainer. I'm your host. I've been a senior network architect and instructor for over 20 years. And today we're going to literally tear into the real world logic of IP routing and wide area networks, or WANs. We're taking those textbook concepts you've been reading up on and applying them to the exact kind of high stakes, sweat inducing situations you are going to face in a real enterprise environment. So let's start with a bit of a mystery, right? Imagine a user at your company's HQ absolutely cannot reach a critical web server at a newly acquired branch office, and that office is thousands of miles away. How does that tiny little packet of data actually find its way across cities, states, or even oceans to hit the exact right server? I mean, it's not magic, right? It's a beautifully structured sequence of logical decisions. But the real question is, when it breaks, how do you fix it? Well, meet Behzad. He's a junior network engineer at a really fast-going enterprise. And he's just been handed this exact troubleshooting ticket. It's high stakes, users are complaining, managers are definitely hovering around his desk, and Behzad has got to figure out why the HQ network is completely failing to talk to the new branch office. Is it a dead physical cable? Is it a bad routing rule? Or maybe a provider issue? To get Behzad out of the hot seat, we're going to follow this troubleshooting roadmap. First, LANs versus WANs, the basics. Number 2, the IP routing logic. Third, encapsulation, changing the envelope. Fourth, reading the routing table. And finally, real-world network troubleshooting. All right, let's jump straight into Section 1, LANs versus WANs, the basics. Before Behzad can even think about fixing that connection, he really has to understand the physical and logical boundaries of his network. Basically, you can't fix what you can't map out in your head. The absolutely crucial starting point is knowing exactly where the LAN ends and the WAN begins. Your local area networks, your LANs, they connect near my devices. Think of the PCs and switches sitting right inside Behzad's HQ building. They use standard Ethernet cables and rely on local MAC addresses to shuffle frames around. But obviously, you can't string an Ethernet cable thousands of miles down the highway to a branch office. That's where wide area networks, or WANs, take over. WANs are your long-haul links. They use routers to bridge those massive distances, using either legacy point-to-point lease lines with protocols like HDLC, that's high-level data link control, or modern virtual links like Ethernet over MPLS. Moving right along to Section 2, the IP routing logic. Okay, now that we know what physically connects the sites, let's look at the actual logical brain behind it. How do Behzad's routers figure out how to push data across the country? This brings us to IP routing, which you'll sometimes hear called IP forwarding. Intuitively, IP routing is just a bunch of independent, disconnected forwarding decisions made hop by hop from the source all the way to the destination. A router grabs a packet, peeks at the destination IP address, checks its internal map, which is the routing table, and just decides where to toss it next. It literally doesn't know the whole path. It only knows the very next step. I always tell my students to think of this exactly like the Postal Service. The IP address, that's the permanent home address written right there on the front of the envelope. It tells you the final, ultimate destination. And the routers are just your local post offices. When you drop a letter in a blue mailbox, your local postmaster doesn't jump in a truck and drive it all the way to a house across the country, right? They read the zip code, put it on a truck heading to a regional sorting facility, which then tosses it on a plane to another facility and so on. Every single router is just reading that address and handing it off to the next logical facility in the chain. Getting a little more technical, a router performs these exact 4 steps, in sequence, for every single packet it touches. First, it receives the data link frame and checks the frame check sequence, the FCS, just to make sure the data wasn't scrambled or corrupted in transit. If it looks good, step 2, it de-encapsulates the IP packet. It literally rips off and throws away the old data link header and trailer. Step 3, it matches the destination IP in its routing table to find the best exit path. And step 4, it re-encapsulates that core IP packet into a brand new data link frame that matches whatever the outgoing interface needs and blasts it out. Now, this is exactly where Behzad got a bit tripped up. And honestly, it's a super common beginner mistake to confuse the hyperlocal role of a MAC address with the global end-to-end role of an IP address. Just remember, the MAC address only ever gets you to the next router on the same local cable. The IP address is what gets you all the way across the globe. Another huge trap, assuming the router is just clairvoyant and magically knows where everything is. Directly connected networks will populate in the routing table automatically, sure, but remote networks like Behzad's new branch office, they absolutely require you to manually add static routes or turn on a dynamic routing protocol. Which brings us to Section 3, encapsulation, changing the envelope. This whole process creates a totally new problem for Behzad to wrap his head around. If the IP address stays exactly the same from end to end, how on earth does the router physically push that packet across completely different types of WAN links? Let's trace the packet's journey looking at encapsulation. Notice how the core IP packet stays perfectly intact. Source IP, destination IP, unchanged. But the outer data link envelope is constantly being stripped off and replaced at every single router hop. From the PC to that first router, it's an Ethernet envelope. The router rips that off, and to send it over a classic leased line, it stuffs the IP packet into a new HDLC envelope. Then the receiving router strips that HDLC envelope off and wraps it in a final brand new Ethernet envelope for local delivery.
And hey, this isn't just for old-school serial links. This applies heavily in modern enterprise networks too. Even if your company is paying for a fancy Ethernet over MPLS WAN link, which basically acts logically like a gigantic Ethernet cable stretched across the country, this encapsulation shuffle still happens. The router grabs the local Ethernet frame from the LAN, completely trashes that local Ethernet header, and slaps on a brand new Ethernet header destined specifically for the MAC address of the router sitting on the other side of the WAN. The data link layer is strictly a hop-by-hop game.
All right, let's dive into Section 4, reading the routing table. Okay, so Behzad firmly grasps the flow of traffic now. The packet goes hop by hop with the IP address calling the shots. So he jumps straight into the router's command line interface to figure out exactly where his packets to the branch office are falling into a black hole. If routers are the post offices, the routing table is basically the set of freeway exit signs the router looks at to find the best path. If there's no sign pointing to the branch office subnet, the router has literally no idea which cable to use, so it just drops the packet and gives up. When he types show IP route in the console, he gets hit with this structured table. Every single line is a route. That protocol code on the far left, that tells him how the router learned it, like a C for connected or an S for static. The prefix is the actual destination network subnet. The next hop IP is the IP of the neighbor router that's going to take the handoff, and the outgoing interface tells him literally which physical port on the back of the metal box the packet is going to shoot out of. So Behzad scans his table and boom, he realizes there is absolutely no entry for the branch office subnet. Let's bring it home with Section 5, Real-World Network Troubleshooting. Armed with this routing table knowledge and understanding how encapsulation works, Behzad is ready to finally squash this bug and prove himself to the team. He logs in and configures the missing static route on the HQ router, pointing it directly to the branch office network. But how does he prove it actually works? He reaches for the network engineer's absolute best friend, the ping command. He pings the IP address of the router on the far side of the WAN. A successful ping is incredibly powerful. It proves the physical cables are good, it proves the layer 2 encapsulation is totally functional, it ensures the subnets align perfectly, and it even proves there are no rogue access control lists secretly blocking his traffic. And the ping succeeds. The users at HQ are back in business, reaching the branch office server no problem. Through this pretty stressful ticket, Behzad actually learned a senior engineer's golden rule, one pulled right from our source text. The network layer thinks about the bigger view of the goal, while the data link layer thinks about the specifics. IP handles that massive end-to-end journey, while Ethernet and HDLC are just doing the grunt work, handling the hop-by-hop heavy lifting. Behzad absolutely nailed this outage using manual static routing, but it definitely leaves us with a pretty provocative thought. As this enterprise scales up to 50 or maybe 100 branches, relying on static, manual routes is going to become totally impossible. What happens when a WAN link gets cut by a backhoe in the middle of the night, and these routers need to learn and adapt to those failures completely automatically with zero human intervention? Well, that's exactly where dynamic routing protocols like OSPF come in, and that is what you should be really excited to tackle next. Thanks for hanging out with me on this explainer, and keep building those routing tables in your mind.